Hey everyone, let's just jump right into it. Today we're decoding a really fundamental industrial mystery, one that basically sits right at the heart of electrical engineering. If you walk onto any major factory floor, you're surrounded by these massive machines, all driven by electric motors. But there's a strict set of rules dictating exactly how these machines are wired up, and it all comes down to sheer physics, high stakes, and honestly, pure economics. So in this explainer, we're going to unlock exactly why high-tension and low-tension motors are treated so fundamentally differently.
Okay, let's dive into this. The whole reason we're doing this deep dive today was actually triggered by this fantastic central question. Why is it that high tension, or HT motors, are normally connected in a star configuration, while low tension, LT motors, are almost always connected in a delta configuration? I mean, it kind of seems counterintuitive, right? That two types of industrial motors would operate on completely opposite foundational logic. So here's our roadmap for figuring this out. First, we'll look at the motor connection standard itself. Then, the insulation problem with HT motors. Third, controlling that HT starting current. Fourth, why LT motors use delta. And finally, the final verdict.
All right, let's start with part one, the motor connection standard. So to establish the universal rules of the industrial floor, we're basically working with a clear binary here. For high-tension motors, the standard is the star configuration. For low-tension motors, it's the delta configuration. Now look, as with any field, there are rare exceptions where you might find an LT motor running in star. But in the vast majority of cases across the industrial world, this is the unbreakable rule. And the cool thing is, if you understand exactly why the HT motor uses star, you'll immediately grasp why the LT motor defaults to delta. Moving on to part two, HT motors and the insulation problem. Now, what's really interesting about this slide is the sheer scale of the power we're dealing with when we step into the high-stakes world of heavy industry. HT motors operate at incredibly high voltage levels. We're talking typically around 6.6 kilovolts, or even up to a whopping 11 kilovolts at their terminals. That is massive. When you supply that much raw electrical pressure, the stator winding inside the motor has to be protected. The higher the voltage level, the stronger and thicker the winding insulation has to be. But here's the problem. Winding insulation is directly tied to the cost of the motor. Manufacturers and customers, obviously, always want to keep costs down, but you absolutely cannot compromise on insulation strength when you're pushing 11 kilovolts. So how do engineers actually solve this wildly expensive problem? Well, the answer lies in the brilliant math of the star connection. When you connect an HT motor in star, just look at the equation. The phase voltage, which is the actual voltage those internal windings experience, becomes equal to the line voltage divided by the square root of 3. To put that in simpler terms, the star configuration literally forces the phase voltage to drop by a factor of 1 over root 3. Because the internal windings are now experiencing a significantly lower voltage than the main input, manufacturers can safely get away with providing thinner, lower-strength winding insulation. This massively reduces the overall manufacturing cost, and it does it without sacrificing an ounce of safety. It's brilliant.
Okay, part 3, controlling HT starting current.
You see, solving the insulation cost is really only half the battle. We also have this universal baseline fact for electric motors. The absolute second you hit start, a motor will draw 6 to 7 times its normal full load current. Seriously, 6 to 7 times. For example, if a motor normally draws 20 amps while it's humming along, it's going to spike to 120 or even 140 amps just to get spinning. Now just imagine applying that massive multiplier to a giant high-tension motor. And this brilliantly illustrates exactly why we just cannot use the delta configuration for HT motors. If you started an HT motor in delta, that 6 to 7 times current spike would be so astronomically heavy that it would trigger a complete catastrophic domino effect. Basically, it creates an extreme voltage dip across the entire system. That dip will instantly trip your HT panels, it'll trip the feeder, and it renders the entire electrical system totally unstable. System crash. By using the star configuration, engineers can tightly control the magnitude of that starting current, which protects the entire industrial grid from crashing. Actually, it's the exact same logic behind a star-delta starter, where you start and star to control the peak current, and then only switch over once the motor reaches, 70 to 75% of its rated speed. This brings us to part 4, why LT motors use delta. So if the star configuration is so fantastic for saving money and protecting the grid, why in the world do smaller everyday factory motors play by completely different rules? Well, to understand this, let's look at this David versus Goliath power rating comparison. HT motors are absolute behemoths, operating at power ratings of 5,000 to 6,500 kilowatts. Huge. In stark contrast, your typical LT motors are tiny, operating at just 5.5, 7.5, or maybe 15 kilowatts. This massive difference in scale literally changes all the math.
Because LT motors have such dramatically lower power ratings, the cost of their winding insulation is pretty much entirely negligible. Remember how HT motors use STAR to save an absolute fortune on expensive high-voltage insulation? Well, for an LT motor, that financial pressure simply doesn't exist. There is just no major cost-saving benefit to forcing an LT motor into a STAR configuration. It's a non-issue.
But wait, what about the current spike? I mean, just like the big machines, LT motors still draw 6 to 7 times their full load current the moment they start, right? They absolutely do. However, because their absolute power output is so small, that initial current multiplier doesn't really matter to the broader grid. The voltage dip it creates is completely negligible. It's definitely not going to trip your panels, and it certainly won't destabilize your whole system. Because there is basically zero risk of a system crash, LT motors are totally free to safely and efficiently operate in the Delta configuration.
And finally, part 5, the final verdict.
Okay, let's pull all of this together. So the crucial point is this. The industry isn't just picking connections at random here. It all comes down to physics and economics. HT motors absolutely must use STAR because it mathematically lowers the phase voltage to save on wildly expensive insulation while simultaneously preventing a massive system-crashing current spike at startup. On the flip side, LT motors use Delta because their power ratings are so incredibly small that the cost of insulation and the risks of voltage dips are practically non-existent. It is honestly fascinating how a supposedly simple choice between STAR and Delta ultimately comes down to protecting the entire electrical grid and keeping manufacturing costs in check. Which kind of makes you wonder, what other universally accepted industrial standards out there are secretly being driven by simple, cost-saving physics? Something to think about the next time you look at a massive piece of machinery. Thank you so much for joining me on this explainer, and keep learning.